Let's explore potential causes and solutions for a significant voltage drop in a residential electrical service. A 2,400 square foot house, wired with 4/0 aluminum conductors running 240 feet to a 200 amp 42 space panel, is experiencing dimming lights when the air conditioner starts. The air conditioner draws 35 amps on startup and 20 amps while running. The wiring to the air conditioner is number 6 copper and runs 60 feet. A load test revealed approximately 110 amps being drawn with the air conditioner, hot water heater, stove, lights, and fans operating. The voltage at the meter is 246 volts, but drops to 231 volts at the panel under the 110 amp load, resulting in a 15-volt drop. The service load was originally calculated to be 102 amps. A key issue is the voltage drop calculation, which initially suggested an adequate wire size. However, this calculation used only the 250-foot distance from the panel to the meter and did not account for the additional 200 feet from the meter to the transformer. Firstly, an oversized neutral wire may exist. If the neutral wire is larger than the hot wires, it can carry more current and create a voltage imbalance, potentially contributing to the voltage drop. Secondly, loose connections could be a factor. Loose connections in the panel, service entrance, or along the service conductors can increase resistance and lead to voltage drop. Thirdly, an undersized transformer may be the culprit. The transformer supplying power to the house may be too small to handle the increased load, particularly during air conditioner operation. Fourthly, faulty wiring could be present. Damaged or degraded wiring can increase resistance, contributing to voltage drop. Fifthly, the long distance to the transformer is definitely a factor. The additional 200 feet from the meter to the transformer significantly contributes to voltage drop. The initial calculation seems correct for the 250-foot distance, but neglecting the additional 200 feet to the transformer underestimates the required wire size. Now let's look at recommendations. 1. Check the neutral wire size. Ensure the neutral wire is the same size as the hot wires, which in this case should be 4/0 aluminum. 2. Inspect all connections. Carefully examine all connections in the panel, service entrance, and along the service conductors, ensuring they are tight and secure. 3. Contact the utility company. Request the utility company to verify the transformer size and confirm its adequacy for the load. 4. Consider a detailed voltage drop study. A comprehensive voltage drop study can pinpoint the exact voltage drop and identify the contributing factors. 5. Upsize the service wire, if necessary. Depending on the voltage drop study, consider replacing the 4/0 aluminum wire with a larger size, such as 350 kcmil or 400 kcmil aluminum wire. Finally, address the failed refrigerator motors. The homeowner's experience with 2 refrigerator motors burning out in the past year is likely related to the voltage drop. Refrigeration motors are susceptible to voltage fluctuations and can be damaged by sustained operation at reduced voltage. Here's a more in-depth look at the calculations and considerations involved in diagnosing and resolving this issue. Let's start with a more precise voltage drop calculation. The initial calculation only considered the distance from the panel to the meter. The total distance from the transformer to the panel is 450 feet. We should use this full distance in the voltage drop calculation to get a more accurate assessment. The voltage drop formula is voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant for the conductor material, I is the current in amps, D is the one-way distance in feet, and circular mils is the circular mil area of the conductor. For aluminum, K is approximately 17. Copper has a K of 12.9. The initial wiring is 4/0 aluminum. 4/0 aluminum has a circular mil area of approximately 211,600 circular mils. Using the 450-foot distance, the 110 amp load, and K equals 17, the voltage drop is 2 times 17 times 110 times 450 divided by 211,600. This equals 33 times 110 times 450 divided by 211,600, which equals 633,500 divided by 211,600, which is approximately 7.72 volts. This voltage drop is for one conductor. Since the voltage drop occurs on both the hot and neutral conductors, you need to double this value. 7.72 times 2 is approximately 15.44 volts. This result aligns with the measured voltage drop of 15 volts, suggesting the initial wire size may be inadequate for the total distance and load. Now, let's examine the effect of the additional 200 feet of 2/0 aluminum triplex from the transformer to the meter. 2/0 aluminum has a circular mill area of approximately 133,100 circular mils. Using the same voltage drop formula, the voltage drop in this section of the service is 2 times 17 times 110 times 200 divided by 133,100. This calculates to 748,000 divided by 133,100, which is approximately 5.62 volts. Doubling this value to account for both conductors, you get approximately 11.24 volts. This means that about 11.24 volts of the total voltage drop is occurring in the 200-foot section from the transformer to the meter. This highlights the significant impact of the distance from the transformer on the overall voltage drop. Now let's investigate further using NEC tables. NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and installation conditions. For 4/0 aluminum, typical ampacity ratings are around 180 to 200 amps, depending on the temperature rating of the insulation. Given a 200 amp service, the 4/0 aluminum conductors appear to be adequately sized for the service ampacity requirement. However, ampacity is only one factor. Voltage drop is a separate consideration, especially over long distances. NEC Section 215.2a-3 addresses feeder conductor sizing and requires that conductors be sized to prevent voltage drop exceeding 3% for feeders and 5% for feeders plus branch circuits. In this case, the 15-volt drop represents approximately 6.1% of the 246-volt supply, exceeding the recommended limit. Now let's consider upsizing the service conductors. To reduce the voltage drop, consider upsizing to 350 kcmil or 400 kcmil aluminum conductors. 350 kcmil aluminum has a circular mill area of approximately 350,000 circular mils, and 400 kcmil aluminum has a circular mill area of approximately 400,000 circular mils. Let's calculate the voltage drop with 350 kcmil aluminum. Using the formula, voltage drop equals 2 times 17 times 110 times 450 divided by 350,000. This calculates to 1,683,000 divided by 350,000, which is approximately 4.81 volts. Doubling this for both conductors, the total voltage drop is approximately 9.62 volts. This is a significant improvement over the 15.44 volts with the 4/0 aluminum. Now let's calculate the voltage drop with 400 kcmil aluminum. Using the formula, voltage drop equals 2 times 17 times 110 times 450 divided by 400,000. This calculates to 1,683,000 divided by 400,000, which is approximately 4.21 volts. Doubling this for both conductors, the total voltage drop is approximately 8.42 volts. This is even better than the 350 kcmil aluminum. By upsizing to 400 kcmil aluminum, the voltage drop is reduced to approximately 8.42 volts, which is about 3.4% of the 246-volt supply, bringing it closer to the recommended 3% limit. In addition to the service conductors, the neutral conductor's role should also be considered. An oversized neutral conductor can sometimes mask issues in the system. Ideally, the neutral conductor should be the same size as the phase conductors, in this case, 4/0 aluminum or the upsized equivalent. If the neutral conductor is significantly larger, it could be carrying a disproportionate share of the unbalanced load current, which can affect the voltage balance. Let's also address the branch circuit wiring to the air conditioner. While the main focus is on the service conductors, the number 6 copper wire running 60 feet to the air conditioner could also contribute to voltage drop, especially during startup. The voltage drop formula applies here as well. For copper, K is approximately 12.9. Number 6 copper has a circular mill area of approximately 26,240 circular mills. Using the formula, voltage drop equals 2 times 12.9 times 35 times 60 divided by 26,240. This calculates to 54,180 divided by 26,240, which is approximately 2.7 volts. Doubling this for both conductors, the total voltage drop is approximately 4.14 volts. This voltage drop is relatively small compared to the service conductors but could be noticeable during the air conditioner startup. Consider upsizing the wire to number 4 copper to reduce this voltage drop. Number 4 copper has a circular mill area of approximately 41,740 circular mills. Using the formula, voltage drop equals 2 times 12.9 times 35 times 60 divided by 41,740. This calculates to 54,180 divided by 41,740, which is approximately 1.30 volts. Doubling this for both conductors, the total voltage drop is approximately 2.60 volts. Now, let's address the homeowner's concerns about the refrigerator motors burning out. Reduced voltage can cause motors to overheat and fail prematurely. When the voltage drops, the motor draws more current to maintain its output power. This increased current leads to increased heat, which can damage the motor windings and insulation. Ensure the voltage is within an acceptable range, typically plus or minus 5% of the rated voltage. For a 120 volt motor, this means the voltage should be between 114 volts and 126 volts. A sustained voltage drop can significantly shorten the lifespan of motors and other appliances. Another important consideration is the quality of the connections at the transformer. Poor connections at the transformer can introduce additional resistance and contribute to voltage drop. Request the utility company to inspect the connections at the transformer and ensure they are clean and tight. Corrosion or loose connections can significantly impede current flow and increase voltage drop. Also, ensure the grounding system is properly installed and maintained. A poor ground connection can affect the voltage stability and contribute to voltage fluctuations. The grounding electrode conductor should be properly sized and connected to a grounding electrode system that meets NEC requirements. Now let's talk about power factor. Power factor is a measure of how effectively electrical power is being used. A low power factor can increase current flow and contribute to voltage drop. Most residential loads have a power factor close to 1, but some appliances, such as motors and fluorescent lights, can have a lower power factor. Improving the power factor can reduce the overall current demand and decrease voltage drop. Power factor correction is typically used in commercial and industrial settings, but it may be a consideration for large residential installations with significant motor loads. Another factor to consider is harmonic distortion. Harmonic distortion is the presence of harmonic frequencies in the electrical system. These harmonic frequencies can increase current flow and contribute to voltage drop, as well as cause other problems, such as overheating of transformers and neutral conductors. Harmonic distortion is typically caused by nonlinear loads such as electronic devices and switching power supplies. While harmonic distortion is more common in commercial and industrial settings, it can also occur in residential installations with a large number of electronic devices. Using power quality monitoring equipment to measure voltage, current, power factor, and harmonic distortion can provide valuable insights into the electrical system's performance and help identify potential problems. This equipment can help pinpoint the sources of voltage drop and other power quality issues. Now let's recap the key steps to address the voltage drop issue. 1. Perform a comprehensive voltage drop calculation, taking into account the total distance from the transformer to the panel. 2. Check the neutral wire size and ensure it is the same size as the phase conductors. 3. Inspect all connections in the panel, service entrance, and at the transformer for tightness and corrosion. 4. Request the utility company to verify the transformer size and inspect the connections at the transformer. 5. Consider upsizing the service conductors to 350 kcmil or 400 kcmil aluminum to reduce voltage drop. 6. Check the branch circuit wiring to the air conditioner and consider upsizing the wire to number 4 copper. 7. Ensure the grounding system is properly installed and maintained. 8. Monitor the voltage of the panel under load to verify the effectiveness of the corrective actions. 9. Address any power quality issues, such as low power factor or harmonic distortion, if present. 10. Advise the homeowner on the importance of maintaining proper voltage levels to protect sensitive equipment, such as refrigerator motors. By systematically addressing these factors, the voltage drop issue can be resolved, and the homeowner can enjoy a stable and reliable electrical supply. Remember to always follow safe electrical practices and consult with a qualified electrician when working with electrical systems.